Hi, my name is Jocelyn Disla, and I will be presenting Credit Loan Approval Prediction. We're going to go over the process and the results of this predictive analysis of loan approval. Credit loan approval is a critical decision for both lenders and borrowers. Lenders want to minimize their risk of default, while borrowers want to secure a loan with favorable terms. However, the traditional loan approval process can be time-consuming and subjective. The goal of this project is to develop a predictive model that can accurately assess creditworthiness and streamline the approval process. This would best benefit lenders such as banks. They would be able to reach more clients since the fear of having their credit pulled will no longer present an issue. In order to build a credit loan approval prediction model, relevant data was collected from Kaggle.com. This dataset is named Credit Risk Analysis. As seen below, it lists over 2,000 entries with 10 features. The features include borrower's credit history, income, age, loan intent, status, and loan default, along with other financial data. Loan default refers to the individual's past loans and whether they defaulted or not. The credit risk dataset was prepared for two models, a logistic regression model and a random forest model. The following steps were performed to have the cleanest, most efficient data. First, the ID feature was dropped from the dataset because it was unnecessary and provided no significance to the credit risk analysis. Next, non-values or unusable values in the dataset were replaced with the average of the values column. Dummy variables were then created for categorical features such as home, intent, and default. Lastly, features in the target variable were assigned to X and Y in order to be able to split the data into a training and test set. The status feature, which is the loan approval status, was set to the target variable. 40% of the data set was used for the test set, and the remaining 60% became the training set. The visualization presented is a bubble chart created to understand borrowers who have not previously defaulted on loans. The size of each bubble signifies the borrower's income. Larger bubbles mean the individual's income is greater than the rest. The loan is described by the x-axis on the chart, and the y-axis describes the borrower's loan amount as a percentage of their income. We can see the smaller bubbles at the top of the chart are a higher percentage of the borrower's income. The loan amount is also higher. The chart basically demonstrates that most of the reasons for loans is the debt consolidation, meaning all of the applicant's debt is combined so that they can make one payment rather than multiples, which explains why the loans are large. Overall, participants are applying for large loans so they can pay one debt off rather than having many small ones. Another trend in the chart is many people choosing smaller loans to be exactly what they need, nothing less and nothing more, since paying it back will be a hassle and constantly taking chunks out of their paychecks. We also see the tiniest little bubbles on the right of the chart on the top, meaning those borrowers have small incomes with large debts. Since many consumers can't buy large price tagged items all the time, being able to pay for it with a loan or paying the loan over a longer period of time allows the product to be more accessible to consumers. There are several models that can be used for this task. The two chosen for this project are logistic regression and random forest. Each model has its strengths and weaknesses, and the choice of model will depend on its performance. A logistic regression model was built to determine whether lenders or companies loaning to their clients should be deterred based on their income or other deciding factors within the dataset features. The random forest model would help in predicting loan status, since this model does well with large datasets. The key benefits to a random forest model are that it has a smaller risk of overfitting the data, its flexibility, and this model also makes it simpler to determine important features. Overfitting data can lead to inaccurate readings as well as predictions because the parameters become biased in the sample that the data is collected from. The algorithms for the logistic regression and random forest models were fit and applied to the prepped and split data using the scikit-learn module. The algorithms find and extract patterns from the data to be able to use those same patterns to predict results. The logistic regression was evaluated first, then the random forest model was evaluated second. A confusion matrix was used to evaluate the performance of the logistic regression. It shows the number of true positives, true negatives, and false negatives. 0 signifies the loan was not approved, and 1 signifies the loan was approved. The confusion matrix revealed the model predicted 10,004 true positives and 469 true negatives for the loan disapprovals. There were also 183 false positives, meaning the model predicted 103 loans were approved, but the actual data stated that those loans were not approved. Lastly, the model predicted 2,377 values were not approved for their loan, but in reality they were. After plotting an ROC curve, the AUC score that was calculated was 0.765. This signifies the model's performance at distinguishing positives and negatives. The score is acceptable but poor. It could be better to be more reliable. However, this model was not ideal for this prediction analysis and therefore would not be continued to be used. The classification report displayed an overall accuracy score of 0.80, a precision score of 0.72, which is the percent of predictions that were correct, a recall score of 0.16, and an F1 score of 0.27 for loan approval within the model. Recall is the percent of the positive statuses that were caught. The scores for loan disapproval within the model were 0.81 for precision, 0.98 for recall, and 0.89 for the F1 score. The F1 score is the harmonic mean between precision and recall, basically the percent of positive predictions that were correct. Feature importance was applied in the random forest model, which gave us all the features from the most important and biggest impact on loan approval to the least important features. The top 3 features were the percentage of the loan compared to the borrower's income, the loan's interest rate, and the borrower's income. The performance of the random forest model was evaluated with a confusion matrix. It indicated that there were 1,907 true positives and 10,047 true negatives for loan approval. If you're following along with the chart, we can also see there were 939 false positives. The model predicted the applicant's loan would be approved when the loan was actually declined. There were also 140 false negatives, meaning the model predicted the applicant's loan would not be approved, but the loan was in fact approved. The classification report that was calculated displayed an overall accuracy score of 0.92. For loan disapproval, we can see a precision score of 0.91 and 0.99 for recall. For loan approval, there was a score of 0.93 for precision and 0.67 for recall, which recall includes information on missed positive predictions, while precision focuses on true positive predictions. Potential loaners should pay attention to their borrower's income and the amount of money they are asking for. The models performed had different outcomes, which conveyed that the random forest model was more accurate, precise, and a better fit for the dataset than the logistic regression model. The borrower's privacy can be an issue ethically, since a person's attributes should not affect whether a company would decline or accept their application, such as their age, home, or employment length. These attributes should not be used to automatically decline a loan because judging someone based off of 1 or 2 defining characteristics demonstrates that the company or lender views themselves as superior to their clients, which is morally dishonorable. This model would allow lenders and banks to fill in information about their clients to see if they are likely to be approved or not, benefiting both the lender and borrower simultaneously since a credit check would not have to be done in this early part of the process. Recommendations moving forward would be to remove irrelevant features from the analysis so that the model can achieve a more optimal performance overall. Digging deeper into the depth of the trees would also help the model improve its performance, specifically finding the optimal number of max depth. Thank you so much for listening in today. I have presented my references below so you can have access to more information on these resources if you choose to.